Yes, hello, good evening, guys. Can you hear me?
Good evening, sir.
Yes, so last class, I think we discussed till first order reaction. Yes. Yeah, so first order we have discussed, graph also we have seen. Next, we are going to start with the second order reaction. So write down the heading. Second order reaction. Okay. So I'm assuming any reaction, for example, or what we can say in this second order reaction, the rate of the reaction depends upon two concentration term, or we can also say the square of the any one concentration term, right? Anything we can say like that. Okay. A few reactions or a few examples of second order reaction we have. The first one is saponification reaction. This is the reaction which gives salt of an ester, salt of when ester reacts with a base. For example, if I write down, one second. Yeah. So if I write down a reaction CH3, C double bond O, OC2H5, ester reacts with a base OH, it converts into CH3, C double bond O, ONA, and C2H5OH. This reaction is a second order reaction. Another example we have 2NO2 gives 2NO plus O2. 2O3 gives O2. Second order reaction. Okay, with respect to this. Now I am assuming a reaction here, and the reaction is a reactant A gives product. Second order reaction we are assuming. So the rate expression would be what? The rate expression for this equals to minus of d concentration of A by dt is equals to the rate constant K into concentration of A square, since we have assumed that the reaction is of second order. Now, one more thing you try to understand here, I am writing down this expression with respect to this reaction. Okay, so if you have reactions like this, for example, if the reaction is given in the question 2A gives product, then we'll write the expression according to this reaction, correct? So don't try to mug up this relation. Try to understand how to write down the rate expression. Yeah, it's first order reaction 2O3 plus O2 if you give. I have just written over here with respect to O3, it is second order. Overall order is, that's what I said. I let down here with respect to O3. Overall order is 1. Okay, 2A gives product. So I'm just trying to make you understand that this expression you don't mug up. Okay, expression will write down with respect to the reaction given. If you take this reaction, if this is given in the question, then here the expression of rate would be R is equals to half of minus of D concentration of A by dt is equals to K times A square. Then minus of D concentration of A by dt is equals to 2K concentration of A square, and then we can solve this by integration. Correct? You must take care of this. Okay, according to the reaction, we'll write down the expression. Fine. So we'll continue with this. So we have the expression which is minus dA by dt minus of D concentration of A by dt K concentration of A square. So when you integrate this D concentration of A by A square, it becomes K dt, right? A naught to AT. A naught is the concentration when time is T, initial concentration. When time is T, this becomes AT. Now you need to integrate this and solve the expression you will get. K is equals to 1 by T, open bracket, 1 by concentration of AT minus 1 by concentration of A naught. This is the expression of K will get.
So could you go to the previous slide?
Yeah.
Thank you, sir.
Yeah. Yeah, Aditya, we can have it tomorrow. Okay, tomorrow you can call me. Aditya C.
Sir,
Correct?
tomorrow is okay. Fine, sir. Okay.
Because I have to go to airport. Okay, like
Yes,
9:30 I have to reach. Okay, so I cannot wait
okay,
much
sir.
today.
No problem, sir.
You are talking about this thing. You have some doubt regarding the test. Tomorrow the test. That's why.
No, not urgent, sir. I
Then
okay.
tomorrow 8
Yeah,
you can
tomorrow
call.
I'll ask, sir. Okay, sir.
Yeah. Okay. Fine. Today I cannot wait because I have to rush to airport. That's the thing. Anyways, so this is the expression we get. Correct. Now, could you tell me what is T half here? At T is equals to T half, the expression we know it becomes half again. So concentration AT at T half would be A naught by 2. We substitute this and we'll find out the expression for T half like we did in other reactions. So here T half would be 1 by K A naught. So here more concentration we take, initial concentration, lesser will be the value of half-life. Okay, because obviously the rate is, if you compare this with the first order reaction, rate is directly proportional to the concentration. Here rate is directly proportional to the square of the concentration. So obviously the reaction is proceeding with a faster rate, correct? So half-life should be lesser than to that of first order. That's why you see inversely proportional. More value of A you get, lesser will be the half-life. Okay, so T half here for second order reaction is inversely proportional to the initial concentration. Okay. Look at this graph here. Okay. So the first graph we are looking at rate and concentration. Rate and concentration, we know the relation, the graph goes like this, because we know R is equals to K times A square. This is the graph we have. Rate and concentration is square. The graph will be a straight line passing through origin. Relation is this only. We have this graph. This graph is for rate and concentration square. So we have this. This one will take y-axis as 1 by concentration of reactant, okay, AT. And this side we have time. So this graph would be, if you draw, it will also be a straight line like this. This L value would be 1 by A naught. What is the graph of T half and 1 by initial concentration? Y-axis is T half and this is 1 by A naught, initial concentration. This would be again a straight line passing through origin, and the slope of this line is what?
1 by K.
1 by K.
1 by K. The slope. Okay, so these are the graphs we have for this. So all these three order reaction we have discussed, 0, first and second. Now we'll see the expression for any nth order reaction. Okay. The last graph, T half, Anirudh. T half is same, no? The relation of T half and concentration, you see. We have done this relation last slide, you check. T half is equals to 1 by K into A naught, correct? So T half and 1 by A naught is what? Y is equals to mx. Slope is 1 by K. Graph is this. Simple, no? Correct, yeah. Okay. Next, write down kinetics of nth order reaction. Nth order reaction. Again, the same reaction I am assuming. A gives product. A gives product. Nth order reaction we have. So rate is equals to minus deconcentration of A by dt K times concentration of A to the power n. Similarly, we can solve this. And when you solve this, the expression would be, I'll write down the expression here. the expression would be 1 by 1 minus n concentration of A t to the power 1 minus n minus concentration of A naught to the power 1 minus n is equals to minus of kt. So, which further we can write A at any time t to the power 1 minus n minus A naught to the power 1 minus n is equals to n minus 1 k into t. Because of this expression, you see, this expression, this one itself, is not valid for n is equals to 1. Just for this expression, I'm writing it on this step, okay? Because this side will have infinity. This is not valid for n is equals to 1. Okay, even here it is also not valid for n is equals to 1. It's not like the entire expression is not correct for first order. Like you see, if you find out t half here, t half for nth order, first you copy down this. Okay. So you find out t half here. T half is equals to, we can substitute at is equals to a naught by 2. So t half could be, I'll write down 1 by n minus 1 into k. At is a naught by 2 to the power 1 minus n minus a naught to the power 1 minus n. Okay, take care of the signs, okay, plus minus sign and all. So when you solve this, you will get t half is equals to a naught to the power 1 minus n divided by n minus 1 into k, open bracket, 1 by 2 to the power 1 minus n minus 1. This is the expression we have. So the point I'm trying to make is, for any nth order reaction, t half is directly proportional to a naught to the power 1 minus n. Yeah, I'll go back, Aditya, just a second. A naught to the power 1 minus n. Done? Okay, so you will get very basic, simple questions on these expressions that we are getting. I'm not going to, give you any questions on this now, because when we do others, concepts based questions like temperature and all, then we'll cover all these concepts there only, right? So here the basic questions based on the relation of K, concentration and time, we are not doing here now. Later on, after discussing few more concepts, we'll cover up those kind of questions also. Okay. So this is the expression we get, and you see T half is this. It is valid for all the value of n here. You see, when n is 0, T half is directly proportional to initial concentration. Fine. N is equals to 1, it is independent. N is equals to 2, it is inversely proportional. Correct? So it is valid for all the, this thing, value of n. There are few reactions which we call it as pseudo first order, because the entire chapter, the most important order is n is equals to 1, first order. All the questions and the further you see the concepts that we are going to see, all these things are based on first order reaction only, mostly. So first order is the most important, and then we have zero order. Second order, nth order, you won't get much question, but second order, at least expression you should know. There are some reactions which appears to be second order or any other order reactions, any higher order reactions, but actually it is first order reaction. These reactions we call it as pseudo first order reaction. Okay, so write down the heading next, pseudo first order reaction. Just you need to know few examples for this, and that is it. Okay, examples you need to know, and there's something called pseudo rate constant that you need to know, and that is it. Pseudo first order reaction, write down in this, due to excess amount of one of the reactant excess amount of one of the reactant, the second order or higher order, mainly second order, the second order reaction confirms to be the first order reaction, or it is behaving as a first order reaction. This is due to the presence of excess amount. First order reaction. Okay, this type of reaction is called pseudo order reaction, hence called pseudo first order reaction. Just few examples you need to know in this. The first one is hydrolysis of ester, acidic hydrolysis. Suppose we have CH3 COOC2H5 present in water, and excess of water we have. In presence of an acid, it converts into acid and alcohol. Acid and alcohol. So for this reaction, if you write down the rate expression would be R is equals to K times concentration of ester into concentration of water. But since it is present in excess, so we have seen that, we observe that, it's a practical thing, we observe that the concentration of this water which is present in excess, it won't affect the rate of the reaction much, okay, and hence we neglect it. So K into this, the concentration we assume to be constant, K into this will give a new rate constant, that is K dash into ester. This is the expression of this reaction. And this K dash is called pseudo rate constant. Pseudo rate constant. You need to know the concentration of water. Yeah, we are just doing the example. Okay, data will be given. If they ask you to compare pseudo rate constant, then accordingly the data will be given. Concentration of water will be given. So you can find out from that. You can find out rate constant K, and then K into H2O is K dash, and then you can find out H2O. Simple thing. Just you need to know what is K dash. K dash is K into H2O, concentration of H2O. The second example we have here is inversion of cane sugar. C12 H22 O11 plus H2O excess converts into C6 H12O6 C6 H12O6. Just a second, guys. I think someone's there. Yeah, C12 H22 O11 plus H2O excess, it gives this. So for this, the rate expression would be same thing. I'll write down the rate final value directly. The rate expression would be R is equals to K dash, the pseudo rate constant, into the concentration of C12 H22 O11. Okay. Esterification of anhydride is also the another example. Examples you have to keep in mind, because sometimes they ask theoretical question, which one of these is this thing, pseudo first order reaction, like this also they ask, mostly NEAT. So the reaction here is CH3CO COCS3 plus C2H5OH, alcohol we are taking in excess. So this gives two molecules of ester, CS3COO C2H5. Here, the rate expression, like we had in the previous one, rate also is K dash into the concentration of anhydride. This is the expression we have. Apart from this, the fourth one we have metabolism of hormones in human bodies. That is also pseudo first order.
So metabolism of hormones.
Yes.
Okay, sir.
Metabolism of hormones in human bodies. Okay, so till now, guys, we had discussed about the reaction and concentration we were talking about, correct? All these first order reaction will have in case of titration also, when volumes are involved, right? Will have in case of growth of, the growth of bacteria, the population growth of bacteria, we can have that. Like I said, in volumetric analysis, we can have it, or when the gaseous phase reaction is given. So when the growth of bacteria is there, then what we need to do? We call it as first order growth kinetics, just a term. The expression, how do we get? We'll see that. In volumetric analysis, at different point, the volume is given, and how do we get the expression of K like we had in first order? In terms of volume, that we are going to see. And when the gaseous phase reaction is there, then how we can relate pressure with the rate constant K. Till now we did with concentration. Okay. So next, write down the first order growth kinetics. Growth kinetics. It's very simple. We'll have the general expression of first order only, but only one change is there. Since the population growth we have, so at point with when the time goes, then the population increases. So in the denominator, we'll have more value. Means the value will increase in the denominator. Like you see, we are talking about the growth of bacteria here. Suppose at time t is equals to 0, we have certain population. That is, suppose A we are assuming. At time t, it suppose becomes A plus X. Okay, A plus X. This is the difference we have in the other reactions, correct? In the previous reactions, you see, with time the concentration is decreasing, correct? That's why we had A minus X. AT is A minus X. But since it is growth population of bacteria, correct? So it is A plus X because the population is increasing with time. So it's the same thing, exactly same thing. You can derive the expression, for first order, but since we have done the derivation already, so I'm not going to do the entire thing again. So here the K value would be, if you recall the expression for first order, it is 1 by T ln A by AT, correct? A naught by AT. So if I write down in terms of log, nothing much, you need to do just this 2.303 by time T log of initial concentration is A, and concentration or population at time T is A plus X. So this is the expression we have. Any doubt in this?
Sir, this will be negative, no, sir?
Yes, one negative sign will be here.
Okay.
Okay. Now, next one is in this, the second type in this is the volumetric analysis. Okay, we can say volumetric analysis, or like in any reaction, if some gaseous product is there on the product side only, then we can take the volume of gas also. Okay, for example, you see next, write down volume related method, volume analysis, anything. Or volumetric analysis, correct? So in this, you can do it in two different ways. One is you can directly memorize one formula that I'm giving you. For example, you see the expression of K here is 2.303 by T log of V infinity minus V naught divided by V infinity minus Vt. All that sign and term will be taken care here. There's no negative sign outside. Okay. Where V naught is what? V naught is the volume given at time t equals to 0. V naught is the volume at t equals to 0. Vt is the volume at t is equals to any time t, and V infinity is the volume at infinite time. Now, what you need to do when you are going to use this expression, whatever volume term is not given, you have to take it as 0. Right? I'm just giving you this to solve the question. How do we get this? We'll do that. I'll just give you one more example how to write down the volume related term over here. So here what you have to just keep in mind, if you remember this formula, suppose V naught is not given. Okay, then what you will do? Suppose if initial volume V naught is not given, then you substitute simply V naught equals to 0 in this expression, the expression of K you will get. Suppose if V infinity is not given, you substitute V infinity is equals to 0. The expression you get, with that expression you can find out the answer, correct? Volume we know, because any reactions it is given at a certain temperature and pressure, right? So volume in that case is directly proportional to number of moles. So volume and number of moles we can directly correlate. Okay. First of all, let me tell you this thing, that this expression, if you remember, right, directly you can use this, and all these value you can substitute according to the data given, you will get the answer. Okay. But suppose if you are not able to, if you think like, okay, how do we memorize this expression? So in that case, what you need to do? It's a simple one. You can easily derive it. See, I'll tell you how. We know for a reaction takes place at a given temperature and pressure. Given P and T. So for any reaction, what we can write, the volume is directly proportional to the number of moles. Okay, so number of moles and volume we can correlate. Okay, for example, you see, if I have this reaction and I'm taking only one gaseous product, N2O5 with gives NO2 plus O2. Suppose we have only oxygen in the gaseous state here, it is given. Okay, then how do we write down the volume expression for this reaction? Okay, so simple here you see, we have initial concentration T naught, I am assuming A naught here, and this is 0. This is 0 initially. At time t is equals to t, this becomes A naught minus 2x. This becomes 4x, and this becomes x here. This becomes x. Correct? Now, when t is equals to t infinity, this becomes 0 because all these N2O5 convert into O2 and NO2. This becomes 0. This will be 2A naught, and this would be A naught by 2. Okay. So if I write down the expression of K in terms of the concentration, it is 2.303 by T log of A naught by A naught minus 2x. One second. Okay, this is in terms of concentration. Now, if you know this A naught, how this A naught is related to the volume, and this how it's related to the volume, we can write down the expression in terms of volume. Correct? So at any time t, the amount that is converted into of N2O5 converted into O2 is this, because we have only gaseous product is O2. So X is the amount of A we have at time t. So I'm assuming corresponding to X, we have certain volume. Okay, that is Vt. So what I'm writing down here, for oxygen gas only, at time t is equals to T, the amount of oxygen gas X, this corresponds to some volume, and that I am assuming as Vt, because number of moles and volumes are directly proportional. At time t is equals to T infinity, what is the value of O2? T is equals to infinity. Value of O2 is A naught by 2. In the reaction it is written. This equals to or corresponds to V infinity, because T infinity we have. So what is A naught from this, you see? A naught is directly proportional to 2V infinity. This, if you substitute in the previous expression, that would be K is equals to 2.303 by T log of A naught is 2V infinity divided by A naught is again 2V infinity minus 2x is 2VT. Correct? So when you solve this, you see 2 and 2 will get cancelled. So expression of K is 2.303 by T log of V infinity by V infinity minus Vt. This expression you get in terms of volume. Okay. Now you see, if you compare the first method that I told you, V naught minus V infinity minus V naught by V infinity minus Vt, and I told you whatever is not given, just substitute it as 0. So for this data, you see, for this data, this given data, what is the value of V naught initial volume? It is not given. So V naught should be what? V naught should be 0. If you substitute this V naught 0 in this expression that I've given you here, V naught you substitute 0, you see you'll get the same expression. This is 0, V naught by V naught minus T. So either you memorize this, if volume things are, it's very clear, like what formula you have to use when volume is given, then you have to use this volume formula. Okay, and this kind of formula we only use when there is only one gaseous product. Okay, write down use when only one gaseous product is there. Or we can also say in this way that gaseous molecule is present only on the product side. Write down the volume expression we use when the gases are present only on the product side. We assume that also to use this expression. Okay. So bacteria and this volume, it's not much important. Okay. But not that difficult also, you can understand it easily. Similarly, we can have one more expression here. That is when the compound is optically active. Okay. So for optically active compounds, what things you have to keep? It is exactly similar to the expression of volume that we have got. Okay. You see this. Next is to determine the rate constant. Rate constant of an optically active compound. So here also all data will be given, just you need to use the formula. And what is the formula? Formula is exactly same like we had in case of volume, 2.303 by T log of, instead of V infinity, we have R infinity minus R naught divided by R infinity minus RT. The least important one, but yes, the formula is this. Same thing, R naught is the angle of rotation at 0 time. I'll write down this. R naught is the angle of rotation at t is equals to 0. RT is the angle of rotation at time t. At t is equals to t. And R infinity is again the angle of rotation at t is equals to infinity. Okay, again the same thing, if any value is not given, substitute it 0, you'll get the same expression. Done? Okay, the last one in this type is the most important one, and that is to determine the, write down, to determine the rate constant of gaseous reaction, gaseous phase reaction. Right, pressure will be given, PT will be given, okay? When pressure is given, total pressure will be given. Means the point I'm trying to make is you just need to know that how to write down the K expression. You don't have to worry about the terms, like what terms are given and not. You can easily find out with the data given in the question. That's not a concern. You just try to understand and focus. Your focus should be that how do we write down the expression of K. Okay. So suppose I'm taking one very simplest example here. The example I'm taking is a reaction we have in which A gas converts into B gas and C gas. All are gaseous reactant gaseous product. It is also possible that only one gaseous product will have. That is also possible. So based on the reaction, you can do all these things. So I am assuming here our initial pressure as P naught, and after some time the pressure of A will decrease because A converts into B and C. So it is 0, it is 0, this is P1 and this is P1. No doubt. Okay. So here you see, if I ask you, what is the total pressure at time t? What is the total pressure at time t? Tell me. The total pressure at t is Pt, and Pt is equals to whatever gaseous molecules are there. Okay, try to understand this carefully. Okay. Pressure is because of only gaseous molecule. So whatever gaseous molecules are there, we have to add the pressure of all gaseous molecules. Okay, means we have to add the pressure of A because A is a gas. We have to add the pressure of B. We have to add the pressure of C, where PA, PB, PC are the partial pressure of A, B, and C. Correct? So here PT is equals to PA is nothing but P0 minus P1, PB is P1, and PC is P1. So total pressure PT is equals to P0 plus P1. Okay, this PT will be given in the question. Okay, PT will be given, and suppose the partial pressure you need to find out. BC ka pressure basically you need to find out. Or they may also ask that what is the pressure of A at time t. So you need to find out that what part of A has been converted into B, so that the pressure of A would be where it is 2P1. P1 and P1 will get cancelled. No, this one, you see, P1 and P1. Aditya, Aditya Manjunath. Correct. Is this correct, guys? Total pressure? Okay. So the thing is, if the question is you need to find out the pressure of A at time t, it means you need to find out P0 minus P1. Pressure of B at time t, you need to find out P1. You need to find out C is also P1 here, right? So because all these are first order we are assuming. So if I write down the expression for the first order, that would be what? That would be K is equals to 2.303 by T log initial pressure divided by the final pressure at time t. This is what we need to do.
So could you please go back?
Just a second. Pressure of A at time t. So I'll write down the pressure of A here like this. This PA means pressure of A at time t. Just a second, I'll go back. Pressure of A at time t.
Okay, thank you, sir.
Okay, done. Okay, done, guys. Can I go to the next slide?
Yes, sir.
Yeah.
Yes.
So this is the expression we have pressure of A at time t. So PA is, we know it is P0 minus P1, correct? PA is equals to P0 minus P1. Okay, so K is equals to 2.303 by T log of P0 by P0 minus P1. Because P1 is the partial pressure, right, of B and C. So your expression should not be in terms of the partial pressure because P1 is not given in the question. PT is given, total pressure. And PT relation we have already. PT is equals to what we have? Just now we have calculated. PT is equals to P0 minus P1. So P1 is equals to what? P naught minus PT. Is this correct?
Sir, PT is P naught.
PT is P naught plus P1 we have, correct? So P1 is PT minus P naught, yeah. P1 is PT minus P naught, and this is plus we have here. So this P1 will substitute here. So K expression would be 2.303 by T log of P naught divided by P1 is this, so we'll get 2 P naught minus PT, correct? So this is the expression we have. So you need to understand to write down this expression. For data, you don't have to worry about. Okay, the data will be given. Whatever point the data is given, for that point we'll apply this condition. That point pressure of A at that point, B at that point, and all. We'll do that. So this is the expression of K in terms of pressure. Any doubt in this? We can also do this in one different way because we know pressure and concentration are also directly proportional. Can I go to the next slide? All of you are done? Okay. We can also do it in this way. Suppose the reaction is this. We have A gas converts into B gas and C gas. So what happens at different time, they'll give you the concentration A naught, 0, 0. At time T, it is 80, 0, 0. And they'll ask you to find out the expression in terms of pressure. Simply we know because it is the concentration given, or suppose if moles also it is given here, then obviously the volume, it is understood and you have to consider the volume 1 liter. If moles is given, then assume volume as 1 liter. Otherwise concentration is given is fine. So we know this fact that pressure is directly proportional to concentration. Like volume we were relating, here pressure and concentration also we can relate. So we can say A naught, the pressure at time T is equals to 0, concentration is this. So this is directly proportional to the initial pressure, that is P naught. Okay, and one more thing, this will have certain concentration of B and C that we do not know. Suppose XX we'll have here. Okay. And AT, concentration of A at any time T, that would be equals to what? Pressure at this point T. So concentration and pressure you can also relate like this.
If moles is given, take volume as 1 liter, sir.
That you can assume. If concentration is given, then that's fine.
Yes, sir.
Okay, and then you can write down the again K expression in terms of pressure because it is directly proportional. We can do that. Understood?
Yes, sir.
Sometime what happens, they'll give you expression like this. I'll go to the next page and show you this. Suppose the reaction is again this. A gives B plus C, all are gaseous product and gaseous reactant. And what they'll do, they'll give you at time T is equals to 0, its concentration is A naught, this is 0, this is 0. At time T is equals to T, this becomes a naught minus x, this is x and this is x, and at time t is equals to infinity, this is 0, this is a naught and this is a naught, like this. And the total pressure will be given, correct? So at 2 points, suppose the total pressure is given, like suppose at this point the total pressure is given, it is P1, and here the total pressure is given P2. Right? Then you have to, because this P1 and P2 is given, then you must write the expression of K in terms of P1 and P2 so that we can find out the other things. Correct. So what we can do here, you see, P1, we know this P1 is directly proportional to concentration at this time. So we can write A minus X plus X plus X, which is P1 is directly proportional to A plus X. That's the one relation we have. Similarly, P2 is directly proportional to, could you tell me? P2 is directly proportional to
2A naught.
2A naught.
2A naught. Correct. This is the second relation. Now, what we need to do that you see, we know K is equals to what? 2.303 by T log of A naught by A naught minus X. This is the expression we have. So A naught is nothing but P2 by 2. So A naught, there is no problem. We can substitute P2 by 2 in terms for A naught over here. And A naught minus X we need to find out. So to find out A naught minus X, what we can do? We can subtract these two. This minus this. So left hand side what we have? P2 minus P1 is directly proportional to A naught minus X. Is this right? Yeah, tell me. Understood? Any doubt? Please respond, guys, quickly.
Yes, sir.
Correct. Now just we need to substitute it here. So K is equals to 2.303 by T log of A naught is P2 by 2 divided by, it is P2 minus P1. Is this right? No, just let me check the previous expression. Yeah, A naught minus X is this, A naught is P2 by 2. Yeah, that's correct. So this is the expression we get. So the expression of K in terms of pressure, the given pressure is 2.303 by T log of P2 by 2 times P2 minus P1. This is the expression we get. Clear? So it's all depends that what is the condition given. Why I have taken here, because we know these at these two conditions only the pressure was given P1 and P2. So I have taken these two conditions. If these two condition is given, then we can talk about these two conditions. Okay, so it's all depends upon what condition is given in the question. You can relate directly concentration with pressure, and then we can write down the expression of K in terms of pressure. Understood? It's completely depends upon that what reaction is given first of all, plus what condition is given. Like if I give you one more, reaction here just for your practice, you just see if the reaction is this. We have A gas gives 2B gas, C gas here. Okay, and the pressure is given at any time t. At any time t, the pressure is PT. Total pressure is PT. initial pressure of PA is given, that is P naught. At any time t, the pressure is given PT. You have to find out the expression of K. And at t is equals to infinity, or I write down this way, wait. At time t, the pressure is P1. This is one question, done. Okay. Another question is, acha, you do this one only. Find out the expression of K. Assume this as PT only so that you can avoid the confusion. Total pressure is this at any time t. You need to find out the expression of K. Obviously, since P naught and PT is given, so you need to find out this in terms of P naught and PT. Yeah. It's done. 2 P naught by 3 P naught minus PT. Okay. Yeah, right. So what we'll do here, we'll write down this is P naught, and initially the pressure of B and C is 0 and 0. If it becomes P naught minus P1, so this becomes 2P1 and this becomes P1. So total pressure PT here at this point would be P naught minus 2P1, P naught plus 2P1, correct? This plus this plus this, P naught plus 2P1. So P1 from this, if you find out, because the P1 is not given, so it is PT minus P naught divided by 2. Now the expression of a K for this reaction is 2.303 by T log of A naught, sorry, P naught by PT, P naught by PT, that is P naught minus P1. P1, if you substitute this, you'll get the answer as K is equals to 2.303 by T log of 2P naught by 3P naught minus PT. This is the expression of K for this reaction. So obviously you see if the stoichiometry coefficient changes, the expression will also change. Even in the question when you solve this chapter, right, the numericals, you will have this kind of options also. Like the reaction is given, A, B, C, D, like this 4 options will be given, right? So this is how we'll do it. So whatever we have done, growth of bacteria, volume and optical activity, rotation and all, this particular thing, the pressure related question is the most important one in this, okay? See this question. Yeah, done.
Some of them.
See, I'll do this, wait. Simple one, the reaction is given. A2 gas gives B gas and half of C2, half of C. Okay. Increase in pressure from 100 mm to 120 mm in 5 minutes. Okay. So we are assuming the initial pressure is 100 mm, right? And it becomes 120 in 5 minutes of this change. Correct? So at time t is equals to 0, I'm assuming there is only A, so P naught, 0 and 0. If it is not mentioned that B and C also present initially, you don't have to consider that, right? In general, the assumption is this only, that we have only reactant at time t is equals to 0. At time t is equals to t, it becomes P naught minus P1. This is P1 and this is P1. Now, according to the given data, we have P naught is equals to 100, and the sum of all these, that is P naught plus P1, is equals to 120, right? So P1, P naught, we know what is P1. P1 is 20 mm.
So for C, isn't it half P1?
Acha, half P2, correct. We have this. Oh, then everything is changed. Oh, I made a mistake. My bad. So half P1 we have, and when we add all these, then we'll get P naught plus half of P1 is equals to 120. So P naught is 100. So P naught, P1 is 40 mm, correct? No? So it's 40. Okay. So we need to find out what? We need to find out the rate of disappearance of A. The rate of disappearance of A is what?
Rate of the reaction.
That is minus rate of A is minus d by dt of A. Pressure, so we can write on pressure also here. So it would be P naught minus P1 by this. Time required is 5 minutes. Change is P naught minus P1, one negative sign we already have, minus P naught divided by the time is 5. Okay, better if you write the average rate, that is delta of pressure of A divided by delta of T. So you'll get this. So it would be 40 divided by 5. So we'll add 8 mm per unit is minute. So it is minute. This is the answer we get.
So they're not asking for the rate at 5 minutes, sir. They're asking for average rate. So they're asking for average rate, not the rate at 5 minutes.
Yeah, obviously, because rate at 5, if you need to find out, then what we need to do, the pressure of A at this time, that divided by this.
Yes.
Rate at that point, they cannot, that it does not make any sense. Rate means what? Over a period of time, how the concentration or pressure is changing. That is the rate ratio.
Yes.
So obviously here it is understood that the change that happens from 100 to 120, what is the rate of that change? That's what the rate of disappearance of it.
Okay. Sir.
If they ask you like this, rate at t is equals to 5 minutes, then that would be P naught minus P1 divided by 5.
Yes. Sir.
Clear? Any doubt in this?
1 second.
This question you see. How do we do this? First order reaction, you need to prove it. This kind of question usually they ask in board exam. Okay, that's why I've taken one. See what you need to do here. If it is first order reaction, then for this data, you'll have the value of rate constant K. So find out for this data, rate constant K, and for the second time again, find out for this data, rate constant K. This must be equal if it is first order. So if it is coming out to be equal, the reaction is of first order, otherwise it is not. Okay, you don't have to, I mean, what point I'm trying to make is this kind of question they won't ask you in a competitive exam because they won't ask you to prove it, correct? They can ask you for the given data, they can ask you what is the order of the reaction like this. So it would be a bit of, calculative, you need to do some calculation into it. Method is this only. For two set of data, if the value of K is coming out to be same, then whatever assumption you have taken, that is correct. Means if this question would be like this, exactly the data is given and except this line, it is written over here, what is the order of the reaction? In that case, you have to assume first, okay, assume the order is 0. Okay, find out K for this data, K for this data. If it is equal, means our assumption is correct. Not equal, then assume order n is equals to 1. Again, you find out this, the same thing, correct? So it will take some time, but the method is this only. So you won't get this kind of question in competitive exam, but yes, in board exam, you may get this. So one question for that. Did you find out what is the value of K you are getting? See, I'll do this. Check. See, we have this reaction. See, how do we do this? You try to understand. This pressure is the total pressure given. Keep that in mind. What mistake you can make, I'll tell you. SO2Cl2 gives SO2 gas plus Cl2 gas. So initially I am assuming it has, obviously it is given. So 180 is the initial pressure. And since it is not mentioned, so I'm assuming only SO2Cl2 is present. Pressure is this. There is no SO2, there is no Cl2. Now, when the reaction proceeds, this SO2Cl2 dissociates X, X, and X. This time, here the time which is required, this time is given. This is at T is equals to 0. And this is at T is equals to 240 second. 240 second. So at this time, the total pressure is given. PT is equals to, and here since all are gases and species, take care of this. If this is not gas, we won't take the contribution of this into total pressure. Okay, small things, but important. Total pressure will be pressure of this plus pressure of this plus pressure of this. That would be 180 plus X. So what is the value of X? Could you tell me? PT is given 244. So value of X would be 64. Any doubt in this? Why we need this X? That's the question, right? Why we need this X? Because when you write down the expression for K, it would be 2.303 by T is 240 log of initial is 180 minus it is 180 minus X we have. So this X must be required, right? So this you need to subtract here 64. Now from this data you will find out K. And the same thing you have to repeat for the second set of data. Means again you can start with from here to here, means assume 600 second. So for the second set of data I'll write down the value of X. SO2Cl2 gas okay. So this is again 180, 0, 0. This becomes 180 minus x, x, x. But this time here I am choosing, the time here is 600 and this time is 0. So x value would be 180 plus x. So 302 minus 180, that would be 122. Okay, so x for this data, we are getting 122. So k is 2.303 divided by t log of 180 by 180 minus 122. From this, you'll get the value of k. So if the k value is same for the both set of data, it means our assumption, that is first order of reaction, that is correct. The value of k you will get here is 0.0018 second. Is this the right answer? You're getting this?
So,
Second inverse? Yes? This is the answer you get. Any doubt in this?
Yes.